This video, I'm going to look at linear differential equations. And linear differential equations are differential equations that can have the form y prime plus f of x times y is equal to g of x. It's called linear because the y prime and the y are to the first power. If one of these was being squared, it would no longer be linear. F of x and g of x can be any functions. They don't have to be linear. They can be polynomials, they can be trig, they can be logs, they can be exponentials. What we're really talking about with a linear differential equation is that y prime and y are both to the first power. So let's look at some methods of solving this. One kind of really interesting method. So first I'll look at a differential equation that you guys have seen before. Y prime equals 5 minus y. Now, last week we saw a method of solving this known as separating the differential equation, getting the stuff with y on one side, the stuff with x on the other. So we could think of this as dy over dx is equal to 5 minus y. We can write that as dy over 5 minus y is equal to dx. We anti-differentiate both sides. We get x plus c on the right side. On the left side, we get negative natural log of the absolute value of 5 minus y. And the negative's there because of the chain rule. We can then multiply both sides by a negative and get the natural log of 5 minus y is equal to negative x plus c, because negative 1 times c is also a constant. We can then say that the absolute value of 5 minus y is equal to e to the negative x plus c, which simplifies to c e to the negative x. And we can absorb the negative into that, get 5 minus y is equal to c e to the negative x, and then we can say that y is equal to 5 minus c e to the negative x as a general solution to that differential equation. Now, I'm going to show you guys a second method of doing this that I think you may like a bit more. Alright, in the second method, what I'm going to do to start this out is I'm going to move the y to the left side of the equation. So I'll have y prime plus y is equal to 5. And what I'm going to do is something kind of clever. Because what I'm going to do is make the left side look like it's the derivative of something. Right now, I've got y prime plus y, and I can add something to this or multiply both sides by something to make this left side equal to the derivative of something. And what I'm going to multiply both sides by is e to the x. So if I distribute this e to the x to all these terms, I get e to the x y prime plus e to the x y is equal to 5e to the x. And if you look at this left side, it's the derivative of something. It is the derivative of e to the x y. And the product rule turned it into what was above it, is equal to 5e to the x. I can anti-differentiate both sides, in which case I get 5e to the x plus c is equal to e to the xy. And if I divide by e to the x, this turns into y is equal to 5 plus c e to the negative x, which is the same solution I got earlier. So the question is, how did I figure out what to multiply both sides by? E to the x worked here, but what will it be in other cases? And I think we'll look at one or two more cases, and it'll become kind of clear what you should multiply both sides by. All right, now here is a new differential equation, and this one is non-separable. You could try to separate it, and it's not going to go too well. But what can we multiply both sides by? And again, we want to look at this left side as being the derivative of something. So what could it be the derivative of? Well, let's think about that. So imagine I've got some function f of x times y, and I'm taking its derivative. What I'll get is f of x times y prime plus f prime of x times y. Well, what we have here, so the difference between these two things is these two terms here is the first term, this came from somewhere. And what it came from is probably, it's left over from the derivative of this. But I want to multiply both of these terms by the same thing so that I can get this extra piece here is the derivative of that. So what I could multiply both sides by is e to the tan of x. And if I multiply e to the tan of x by every term here, something nice happens. This left side is now the derivative of something. It is the derivative of e to the tan of x times y. And the left and the right side in this case happens to simplify to e to the first. So how did I choose e to the tan of x? Well, I knew that this secant squared came from the derivative of this exponent here on e to the tan of x. And if we anti-differentiate both sides, we get e to the tan of x y is equal to ex plus c. And if we divide both sides by e to the tan of x, I get y is equal to ex plus c over e to the tan of x. So this is the solution to this differential equation. So in general, if I've got a differential equation of this form, I could multiply everything by e to the integral of f of x. E to the integral of f of x. E to the integral of f of x. Because that will make it so that this left side is then the derivative of y times e to the integral of f of x. Because once I take the derivative, I end up with this coefficient of f of x. Okay, I want to look at this differential equation, which we saw similar to one similar to this on a homework a couple nights ago. That y prime is equal to x minus y. Here is what its slope field looks like. And looking at the slope field, you can see a few things. One is that when x and y are the same, the slope appears to be 0. Another thing that seems to be happening here is that there is this one solution that is linear. And it looks like it's got a slope of 1, and it looks like it goes through the coordinate 0, negative 1. So it looks like the equation of that is y equals x minus 1 is one solution to this differential equation. And what I've done is I've plotted a few possible solutions onto this slope field. And there we are. And there's also a few, on the email I sent, there are some links to a Desmos app where you can change the value of the solution to this differential equation. But don't go there quite yet. And what you'll be able to do is when you change the value of c on that, you'll see these different solutions. But let's solve this differential equation first. All right, so the first thing I'm going to do is I'm going to move the y over, and I'll have y prime is plus y is equal to x. And I'll multiply both sides by e to the x. I chose e to the x because the coefficient of the y here is just simply is a 1. And the integral of 1 is just x. So I multiply both sides by e to the x. So the left side I can think of it as the derivative of e to the x times y is equal to x e to the x. And if I anti-differentiate both sides, the left side becomes e to the x. And on the right side, I have to use integration by parts to solve that. And once I do, I get e to the x minus e to the x plus c. And then I can divide both sides by e to the x. And when I do, I get y is equal to x minus 1 plus c over e to the x plus c e to the negative x as the general solution to this differential equation. And again, what I can do is I can see that one of the solutions is when c equals 0. When c equals 0, this goes away, and I get the solution as one of the solutions. You want to look at this with varying c using animated, you can look up Desmos. But it is a pretty wild solution to that differential equation. It's unexpected, and it's one that you can't get by separating the variables. Now here's one that looks, at first glance, like it's really a pretty tricky problem. Well, the first thing I want to do is I don't want any coefficient of the y prime, of the first derivative. So I'm going to divide everything by x squared. And I'll get y prime equals y prime plus 1 over x y equals 3 over x squared. And again, at first glance, this looks more complicated. But if I think about what I want to multiply both sides by, I can look at the coefficient of the y term, and that's 1 over x. And I think about the antiderivative of 1 over x, which is the natural log of x. So I can multiply everything here by e to the natural log of x. 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 But then if I realize that e to the natural log of x is just x, I'll end up with x y prime plus y is equal to 3 over x. And that's because e to the natural log of x is just x. So I really just had to multiply everything by x. And I get this differential equation right here. And I can see that this is, the left side is the derivative of x, y is equal to 3 over x. Now if I anti-differentiate both sides, I get xy is equal to 3 natural log of x, well, the absolute value of x, plus c. And if I divide everything by x to solve for y, I get that y is equal to 3 natural log of the absolute value of x plus c all over x, which I've also made a Desmos app for this, where you can play around with different values of c to see how different the various solutions of this differential equation look. That link is in the email. Another thing to note is whether or not you have the absolute value there. This thing is undefined at x equals 0, so we have to kind of consider the two different cases if we're actually solving this differential equation. Again, this is one of the more subtle things to solve in these differential equations and to think about, but really we'd have to consider x being positive, x being negative as two different cases. And if we only have a given solution on one side, if I'm given the point 4, 3, that's on the right side of x equals 0, so I can only solve it then for values that are greater than 0. I can't think about values of x less than 0 because that c could be different on that side of the discontinuity. Okay, lastly I want to look at this differential equation, and what I'm going to do is, well, I'd multiply by the e to the integral of the coefficient of y. In this case, I would multiply by e to the 1/2 x squared. So I'll multiply everything by e to the 1/2 x squared, e to the 1/2 x squared. So the left side is going to be the derivative of e to the 1/2 x squared times y is equal to 2e to the 1/2 x squared. Now, we've got a little bit of a problem, and that's that I can anti-differentiate the left side, but I can't anti-differentiate the right side. That does not have a nice antiderivative. So the only thing I can do on the right side is to write it as the integral of 2e to the 1/2 x squared, and then I'll say separately plus c is equal to e to the 1/2 x squared y. So the best I can do for this solution is to write y is equal to the integral of 2e to the 1/2 x squared plus c all over e to the 1/2 x squared. And that is how I have to write this solution. I have to write it in terms of an integral, which is okay. All right, I hope all this helps. Do this next homework, and hopefully at some point I will see y'all back at school, and we won't have snow days forever and ever. So anyway, hope this helps, and see you soon.